more kind of heavy into the physiology, but I think it's really interesting stuff as well. So hopefully you think it is too. I know that you guys are all anxious for lecture exam scores. I'm sure you're chomping at the bit for lecture exam scores. Ran into a new roadblock. So I was looking at Scantrons the other night after I kind of had everything tabulated. There's a whole bunch of students who, not a whole bunch, but a few students who didn't complete their Scantron. Like some people left 10 or 15 questions blank. I've emailed them, so if I didn't email you, it's not you. What we need to do is we need to take some time to correct those so I can post accurate exam scores for everybody so that we can do that. And we should get that concluded today. So if it isn't one thing, it's another. But exam scores will be posted soon. I know that you guys are all really anxious for those. All right. So with that said, let's go ahead and kind of move on to some other stuff. So on Wednesday, we had talked about the heart, and we had talked about the structures that we find in the heart, and we had talked about the pathway of blood flow through the heart as well. And I had asked you guys to spend some time between Wednesday and today sort of making sure that you understand that, right? Well enough that you could pass a quiz on it. That was the goal. So you ready for a quiz? You guys ready? Are you ready to rock and roll? Yeah? Let's do it. Let's do it. I'm just kidding. I don't like pop quizzes. But I like the confidence. I like the confidence. I like the head nods that say yes. My lab yesterday was like, let's do it. And I was like, I'm not ready with the quiz. So I wasn't quite there. But the goal was to be ready for a quiz, right? And hopefully you're feeling confident enough in that, because now what we need to do is we need to start to talk about how the heart actually contracts, right? So we spent time talking about the pathway of blood flow. We understand where we find oxygenated blood and deoxygenated blood. Now we need to start talking about how the heart actually contracts. So one of the really unique things about the heart, as opposed to just about any other organ or tissue in our body, is that it basically has the ability to set its own rhythm. The heart has two clusters of pacemaker cells. These are called pacemaker. They're also called autorhythmic cells. Pacemaker or autorhythmic cells have the ability to depolarize at a really regular rate. And you guys told me that when muscle cells depolarize, they contract, right? So the heart, as a result of these autorhythmic cells, they contract at a really regular rate. These pacemaker cells have kind of a curious developmental origin. They appear to be cardiac muscle cells, but they don't actually contract. So if we were to look at one under the microscope, you might say, oh, it looks like a cardiac muscle cell. But it doesn't actually have the ability to contract. So they're non-contractile cells. They're non-contractile cells in the heart. And they launch, or I don't know what word we want to use. We'll use launch, I guess. Action potentials at regular intervals. Okay. Those pacemaker cells are localized into two clusters in our heart. We have a cluster very near the top of the right atrium. You see it right here. This is called the sinoatrial node. Sometimes we just abbreviate it. Well, usually we just abbreviate it as the SA node. And then the other one that we see is actually right below it. It's not terribly far away. We have the atrioventricular node, or the AV node, right here. So those two clusters of autorhythmic cells are found fairly close to each other. Okay. So what happens is that they launch action potentials. Okay, they launch action potentials, and when the SA node launches an action potential at around 70 times per minute or so, what it does is that action potential spreads to the neighboring myocytes in the heart. How does it spread? What feature of cardiac muscle allows that action potential to spread through the heart?
Gap junction.
Gap junctions, right? The intercalated discs that we saw the other day, right? So those gap junctions, or intercalated discs, allow that action potential that originates right here, they allow it to spread through the atria, okay? So what we can do is we can come over here. We can put that up here, right? We have the SA node, right? We have the SA node right here. And then it spreads through the atria via what we call something the internodal pathway. And eventually, the action potential is going to affect the atrioventricular node. So both of these clusters of autorhythmic cells do launch action potentials at fairly regular rates. But they actually are a little bit different than each other. But we need, and we haven't talked about the cardiac cycle yet, we'll talk about it today, but we need the atria and the ventricles to contract at the same rate, right? If the atria are contracting at 60 beats per minute, the ventricles also need to be contracting at 60 beats per minute. If they aren't, it makes for a mismatch that creates a pretty inefficient pump. So we need them to contract at the same rate. So the SA node and the AV node do contract at slightly, or I guess depolarize at slightly different rates. But because the SA node is above or upstream of the AV node, what's going to happen is that it essentially kind of overrides the rhythm of the AV node, and it sets it to that of the SA node. Okay, so the SA node is what we often call the pacemaker of the cell, okay, or the pacemaker of the heart. So the internodal pathway affects the ventricular node. Then we have to depolarize the ventricles, right? And when we saw the difference between the atria and the ventricles the other day, we saw that the ventricles were a lot more muscular, right? There's a lot more myocardium in the ventricles than there are in the atria. The atria were relatively thin-walled. They were definitely a lot smaller than the ventricles are. When we looked at the heart from the outside, we saw that the majority of the heart was ventricles, right? So it's just for lack of a better term, the ventricles are just a meatier part of the heart, right? So we still have gap junctions between those cells, but we need help to get the action potential through the heart as quickly as possible. So in addition to the gap junctions that we find between the myocytes and the ventricles, we also have a little kind of what appears to be a nerve network through the heart. You can see it on the diagram over here. That nerve network leads away from the atrioventricular node. There are nerve fibers in this structure called the bundle of His that we see right here. It's also called the atrioventricular bundle, or the AV bundle, but we kind of traditionally just call it the bundle of His. And that bundle of His leads down the interventricular septum, eventually branching into right and left bundle branches. And then as those fibers get smaller and smaller and smaller at the apex of the heart, they become what we call Purkinje fibers. Okay? And those Purkinje fibers innervate the outer walls of the atria as well as the papillary pieces. Okay? So the AV node, leading away from that would be the bundle of His, the AV bundle. And then we would have, sorry, we have right and left bundle branches. And then we have who do you think discovered them? I'm really surprised with Smith. So the Purkinje fibers. Okay? You'll notice that those Purkinje fibers do innervate the papillary muscles as well as the wall of the atrium. So in addition to the gap junctions, this, what we call this nodal system of the heart, really ensures that those action potentials spread evenly and quickly to the ventricles, which again are a lot meatier than the atria. Okay. Are there any questions about sort of the anatomy of what we're looking at here? We're all good? Okay. So what I would like to do, if we're all good on this, and the concept here, is I would like to look at the action potentials in the AV node and the SA node, right? So what does an action potential look like in a pacemaker cell, okay? Why does it have that ability to set off an action potential at a really regular rate, right? Neurons don't do that, right? We looked at the action potentials in neurons in 50A, and you know that unless it's stimulated, a neuron stays at resting membrane potential kind of like forever, right? Or very nearly so, I suppose. Has to be stimulated to set an action potential. But these guys have no external innervation at all coming from anywhere else in the body, yet they're able to launch an action potential at a really regular rate. So why is that? That's the first question that we want to answer. And then the second thing that we want to do is we want to look at the action potential in a cardiac muscle cell, okay? So once that action potential leaves the pacemaker and goes to a cardiac muscle cell, what does the action potential look like there? This is not something that you looked at in 50A when you did skeletal muscle. At least I doubt that you looked at action potentials in skeletal muscle. You looked at what they did. They were releasing calcium from the sarcoplasmic reticulum. They were, allowing actin and myosin to interact with each other. But I doubt you looked at the actual action potential, right? So a little bit different today because we want to look at it in the muscle. But let's start with our pacemaker cells. Okay? Let's look at why our pacemakers are able to launch those action potentials at a fairly regular rate. Okay. So let's go ahead and look at action potentials. In auto No, that's not right. You know, I can spell, I swear. It's just early on a Friday. There we go. I know it's hard to tell by looking at me now, but when I was younger, I used to be kind of awkward. Fun fact, when I was in the 5th grade, I almost won my school spelling bee. But you didn't know that? Yeah, I did. I decided I was going to compete in my school spelling bee. And so, has anybody ever done a spelling bee in here? No? You know the book that you get when you compete in the spelling bee, they give you the book of words that you might be asked? And that's all it is. It's just a book, and every page is just filled with the words that you might be asked. Man, I spent weeks with that book. I went in before school every day and studied with my teacher. I went in at lunch recess and studied with my teacher. I came home and had my parents quiz me. I was ready. I'd been training for months for this spelling bee, and I was going to win. So the day of the spelling bee rolled around, and everybody who's competing in the spelling bee is up on the stage, and they bring the whole rest of the school in, and they sit them on the floor of the multi-purpose room. I don't know if you guys had that experience in elementary school where you'd sit on the floor of the multi-purpose room for hours on end. It felt like your butt was going to die by the end of it, but you weren't allowed to get up. So at any rate, I got a chair. I was on stage. It worked out pretty well. That's not why I competed in the spelling bee. But anyway, I was just like destroying the spelling bee. I was just killing the spelling bee. I knew every word, right? And like other people who hadn't studied as much were getting out like left and right. So I don't know how many of us started, but there was like 20, 30 kids in the spelling bee, and I'm just left and right, just knocking the words down, right? Disassociation, boom, got it, tumultuous, boom, got it, whereas other kids are getting out with like cognitive, and I'm like, how do you not know how to spell cognitive? You're in the 4th grade, come on, man. Anyway, it was just, a bloodbath. Anyway, as people get out, they go and sit down in the audience, back with their class and stuff like that. And we got to a point where there was like me, 3 other people on the stage. I was prepped. I was positioned to win the spelling bee. And I looked at the other people on the stage, and I realized I was the only boy up on the stage. And all of a sudden, it got really awkward and nervous. And I looked out I'm 10 years old, right? So I look out in the audience, and I see my friends sitting out in the audience. I wanted nothing more in that moment than to go sit with my friends. So when it was my turn again, I walked up to the microphone, and they gave me my word, salmon. And I looked at the judge, and I said, salmon, S-A-M-O-N. And as confidently as I possibly could, I threw the spelling bee. I'm sorry, that's incorrect. You can go sit with your friends. And I went and sat with my friends. And in that moment, I was very happy. But I look back on it, and here I am, 30-some years later, telling my class about the day that I threw the spelling bee. Anyway, I can spell, I swear. I practiced. In the 5th grade, I knew every word in that book. All right, let's go through the action potential and the autorhythmic cells. Okay. There's a lot going on here. Let's go ahead and make an axis, and let's go ahead and talk about what's happening. All right, I'm gonna give myself a little bit more room. So we're gonna do this. We're gonna label our axes here. This is membrane potential. Okay, membrane potential measured in millivolts. And this is time, right? We're not gonna put any labels on time, but we'll just go ahead. Milliseconds works just fine, right? So this axis should look familiar to you. So you guys will remember in a neuron, the resting membrane potential was around 70 millivolts. Cardiac pacemaker cells, autorhythmic cells, are a little bit different. They have a resting membrane potential of around minus 60 millivolts. So I'm going to go ahead and put minus 60 on here, and then I'm going to put minus 40, and I'm going to put a positive 20 up here. And that should get us what we need out of this. Okay. 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 And then we're going to go ahead and start to draw action potential on this guy. So I'm going to put a dotted line across at minus 60 so we can remember where that is on our way across here. And then I put minus 40 on here because that's going to be what we call threshold voltage. You guys remember threshold voltage from neurons because that's where your voltage-gated sodium and potassium channels are going to become, well, specifically your voltage-gated sodium channels are going to become activated, right? So we're going to go ahead and put a dotted line there. This is going to be our threshold voltage right here. Okay, and then this is resting. All right, so let's go ahead and go through this really quick then. So what we have is we have a situation. Let's just say that we're at resting membrane potential here at around -60. Okay. Our cardiac pacemaker cells have ion channels on them that are exceptionally leaky to sodium and potassium. Okay. What happens if you're leaky to sodium and potassium is what? Where is sodium going to go if your cell is leaky to that? The sodium is normally found where in a resting cell? It's found outside the cell, right? It's found outside, okay? So if your cell is leaky, sodium's going to leak in, right? And sodium's going to leak into the cell. And potassium is normally found where? It's normally found inside. So if the cell's leaky, it's going to be found, or it's going to be leaking out, right? So these channels are sodium-potassium channels. Sodium and potassium can go through them, but they're just really, really leaky, okay? Which do you have more of? Do you have more sodium or potassium? Way more sodium, like 20 or 30 times more sodium, right? So what's going to happen then if you're leaky to sodium and potassium is we're going to see that there's a net depolarization of the cell, okay? So that's what we see happening right here is we see that leakage of sodium and potassium, okay? So let's go ahead and kind of annotate this. I'm just going to go ahead and put a little 1 right here, and then we'll come over here and we'll explain what's happening. If I try to explain it on the graph, it'll be a little bit challenging, right? So we're just going to go ahead and do this. So we see that we have the opening at -60 millivolts. Let me do that. At -60 millivolts, we see that these channels called IF channels open, okay? Open, and that leads to sodium, potassium leakage. Okay, that leads to sodium and potassium leakage. IF channels. Why in the heck did we name these things IF channels? It's kind of a funny story. So you guys are going to get another little bit of Trivial Pursuit here. Okay. In the electrical world, both for electrical physiology and even electrical work, if you were wiring a house or something like that, we use the letter I to abbreviate electrical current. Okay. Current is important for powering appliances in our house, but on the simplest terms, electrical current is electrically charged ions flowing from one space to another. And that's exactly what's happening here, is we see that sodium is leaking into the cell and potassium is leaking out of the cell here, right? So this movement of ions is electrical current. Really no different than what's happening in the wires in your house. It's just on a way smaller scale, okay? So we use that letter I to describe that. So that's where the I comes from in IF channels, is it's referring to electrical current, the movement of ions, okay? What about the F? Well, when we first discovered IF channels, we didn't know what the hell was going on. Physiologists had never seen anything like this before. And I think a physiologist somewhere said, huh, that's funny. And the name stuck. So the F stands for funny. So these are literally called funny current channels, IF channels, right? So that's how they get their name, because the F stands for funny. They're funny current channels. Because when we first discovered them, we'd never seen anything like them. We didn't know how they worked or what was going on or anything like that. And just for lack of a better term, we said, that's funny. And kind of just kept going, I guess. I don't really know. So I don't know if that fits into the category of physiologists being entirely unreasonable people. But sometimes physiologists have a sense of humor, for sure. All right, so these funny current channels, these IF channels, open at around -60 millivolts, and they allow for the leakage of ions. But remember, there's way more sodium leaking than there is potassium, So we see this kind of net depolarization that occurs. Okay. At around minus 40 millivolts, we hit threshold voltage. Okay. And that threshold voltage is going to cause the IF channels to close, but it's also going to cause calcium channels to open. Okay. So let's go ahead and just kind of write that down here. Let's go ahead and just annotate that, and then we'll draw it on the board. So at number 2, we're going to say here that IF channels close at about minus 40 millivolts, but the calcium channels open. Calcium. We haven't seen calcium yet. The action potentials you guys are used to seeing are sodium and potassium. We haven't really talked about calcium yet, right? But calcium, at the end of the day, is still a charged ion, right? So it's really no different than sodium or potassium. It has an electrical charge associated with it. And most of it in a resting cell is found outside of the cell, just like sodium, right? So your extracellular fluid has a lot of sodium in it and has a lot of calcium in it, okay? So when these calcium channels open, calcium's going to rush in to the cell. And that's going to cause the cell to depolarize, just like sodium does, right? So what we see is we see a depolarization that occurs, right? And it's pretty rapid. There's actually a little bit of a bend in the curve right here. And then we see, woo, all of that calcium rushes in, okay? So here, what we're going to do is we're going to say that we see an increase in calcium flow. Whoops, Ca2 plus. There we go. Ca2 plus, an increase in calcium flow into the cell. Okay. And those are voltage-gated calcium channels. So they open and close in response to changes in membrane potential. Okay. You guys with me so far? Yeah? All right. And around positive 20 millivolts, we see that those calcium channels start to close. Okay? So at around positive 20 millivolts, we see that those channels start to close, and we see that potassium channels open. So now we see that the curve turns around. Let's go ahead and annotate that for number 3. I'm going to come over here for number 3. We're going to say that at about positive 20 millivolts, around positive 20 millivolts, calcium channels close, but potassium channels open. Okay. At around positive 20 millivolts, we see the calcium channels close and potassium channels open. And as a result of that, we're going to see that the cell repolarizes. Now we have potassium running back into the cell, and we see that that relative difference between the inside, or I'm sorry, out of the cell, and we see that we have a repolarization of the cell. Okay? So increase in potassium, okay, is what we see happening right here. Okay? When we get down to minus 60 millivolts, we see that the potassium channels close and the IF channels open again, right? So we see that the potassium, let's call this number 4. Here we go, number 4. We see that at minus 60 millivolts, Gesundheit, at minus 60 millivolts, potassium channels close and IF channels open. And then what do? We start to see leakage of ions again, and the whole pattern repeats itself. So unlike with neurons, we don't get back to resting and wait for another stimulus to come in. we just depolarize again right away. Okay. So again, this happens around 70 times per minute. So this entire thing is probably just a little bit less than 1/60th of a second is about how long this entire thing takes, right? If we're doing it 70 times per minute, then that's a little bit less than a 60th of a second that it takes for us to do this, okay? And then it starts again, okay? The pattern repeats itself. But because it never really sets at resting membrane potential, and it just starts to depolarize again right away, we just have action potential after action potential after action potential, all the way, for forever. When those are in the SA node, that affects the entire node. When it affects the SA node, that affects the entire heart. And we know that the heart is going to contract as a result of that, right? Okay. Are there any questions about action potentials and pacemaker cells? It's not a whole lot different than action potentials elsewhere. We have a depolarization and a repolarization. We just have different ions kind of playing the role here, right? Yeah.
So all of this is happening in the cardiac muscle cell? In the cardiac muscle?
Cardiac pacemaker cells. So either in the SA node or the AV node. Okay? We haven't gotten to muscle action potentials yet.
Oh, okay.
Yeah, this is all the autorhythmic cells. This is the pacemaker cells. Just those two little clusters.
Okay.
Yeah. Okay. 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 So again, this can happen in the absence of any external innervation. In our last unit, I had described to you the lab that we used to do where we would, take a turtle or a frog or something like that and take the heart out. And it'll literally beat for hours as long as it has the right ions available to it. So it has to be in some sort of a fluid, but the heart will literally beat for hours once it's taken out of the animal. It doesn't need external innervation to do this. It really just needs the right ions to be able to do it, sodium, potassium, and calcium, and it's going to basically run for a very long time before the tissue actually dies, okay? So, but we do know that the autonomic nervous system can affect the rate at which this happens, right? We know that sympathetic innervation speeds your heart rate up. We know that parasympathetic innervation slows your heart rate down, right? So really what that's doing is it's speeding up or slowing down this process. That's what it's doing. How fast are these pacemaker cells depolarizing? So how does that look and how does it work? So the autonomic nervous system, as I said, the autonomic nervous system controls this process. So the sympathetic nervous system speeds it up. Okay? So sympathetic innervation. Sympathetic innervation. What it's going to do is it's essentially going to increase the cell's permeability to either sodium or calcium, or both. Okay? So it increases permeability to sodium and calcium. Okay? Sodium and calcium. So how would that work? Okay, why is increasing permeability to those ions going to speed up heart rate? Okay. Well, let's take a look. All right, where is sodium flowing? Sodium's flowing in right down here through those IF channels, right? If I increase the permeability of the cell to that sodium, that means the sodium is going to flow faster, right? So what's going to happen is that the graph is going to look like this, okay? And then look, I reach with epinephrine and norepinephrine under sympathetic innervation, I reach threshold voltage here. Without sympathetic stimulation, I reach threshold here. If this is time, that means that I'm reaching threshold in a shorter amount of time, right? And that speeds up my heart rate. The same thing is true for calcium. This is my slope with calcium. That's going to go even faster if I increase the permeability of the cell to calcium, and now I'm repolarizing the cell faster than I would be otherwise. So that means that this whole process happens in a faster pace. Does that make sense? Okay. So sympathetic innervation increases the cell's permeability to sodium and calcium. Parasympathetic innervation, what do you think it does? Does slow it down. How do you think it does that? Increases the cell's permeability to potassium. Increases the cell's permeability to potassium. How would that work? The big change is down here with the IF channels. If I increase the cell's permeability to potassium here, what's going to happen is that I'm going to have more potassium flowing out of the cell with the same amount of sodium flowing into the cell. So I'm actually going to see a slower approach to threshold, and it's going to take longer to get there. Okay? And that's going to slow down my heart rate. Okay? It's going to take longer for that process to occur because the potassium is for lack of a better term, fighting the sodium a little bit more. Okay, so it's going to slow down that process, and we're going to have a slower heart rate as a result of that. Okay. Yeah. So remember that you have both sodium and potassium flowing across the membrane here, right? The depolarization, the movement up, is because there's way more sodium than there is potassium. But if I all of a sudden have more potassium flowing out of the cell, what that's going to do is it's going to kind of dampen the effects of the sodium and cause it to depolarize slower, right? So instead of depolarizing at this rate, it's going to depolarize a little bit slower, okay? One year I made my wife a Valentine's Day card, and it said, "Baby, you make my heart more permeable to sodium." And she didn't really appreciate it, like for what she should have. You know, I thought it was really creative and one of a kind, but she didn't really appreciate it. I had to explain it to her, and the second I started drawing graphs, it kind of ruined Valentine's Day. Don't you see how it increases your heart rate? I don't understand why you don't understand this. I think you're all right. Any questions about that? Probably lots of questions. You're going to have to go through this a few times, right? I don't expect it to be crystal clear the first time around. I fully expect that you're going to go home and review it and you're going to understand it with a little bit more depth. But it's really neat to see what happens. And I personally am very fond of those IF channels. I think that they're almost cute. All right, so let's go ahead and take a look then. So we know that once those action potentials start in either the SA node or the AV node, we know that they're going to spread to cardiac muscle cells. So what I want to do now is I want to look at the action potentials in the muscle cells themselves, okay? And we'll look very briefly at the contractile process as well. You guys actually know most of the story for the contractile process because it's very similar to skeletal muscle. So I'm not going to go into it in a whole lot of detail. But I want to look at the action potentials because this creates the action potentials give the heart a really unique feature. And I think that it's a really important feature for us to understand. So let's draw another axis here, and let's say that we're now going to look at the action potentials in cardiac muscle cells. Let's look at the action potentials in cardiac muscle cells. Again, we're going to need an axis for this, so let's go ahead and draw our Y and our X axis. We're going to label them. Membrane potential measured in millivolts, and we've got time measured in milliseconds. Okay, so we've got our axis here. And we're going to put some numbers on here. So all of these cells are kind of unique in terms of their ion concentrations and things like that. And what that does is it ultimately affects resting membrane potential. So we know neurons have a resting membrane potential of around minus 70 millivolts. We just saw that our cardiac pacemaker cells have a resting membrane potential of around minus 60 millivolts. Cardiac muscle cells have a resting membrane potential of around minus 90 millivolts. So we're going to go ahead and go a little lower on our x-axis or our y-axis here, and we're going to kind of go up from there. I'm going to go minus 80, minus 70. I'm obviously not to scale here, and that's okay. All the way up to positive 20 millivolts that we see right here. Okay. So it's a little bit different, and I'm going to go ahead and put my dotted line here for minus 90 roughly. It's resting right here.
I have a question.
What's that?
What is the 100 at the bottom?
It's just my OCD at work. I just needed to put a minus 100 because I wanted to put even
That's
numbers
because
there.
the minus isn't there.
Oh, sorry. That's your question.
Yeah.
There you go. Now you got a minus 100. That's your OCD at work. Okay. Okay. So, action potential starts in the autorhythmic cell. Again, remember, no neurotransmitters here, okay, because we have gap junctions between all of these cells. So that action potential spreads into a cardiac muscle cell. That cardiac muscle cell is sitting there at minus 90 millivolts, but now we're going to depolarize the cell. So what do we do? Okay. Well, what we're going to do, so we're sitting here at resting membrane potential. There's no IF channels here. This guy can actually sit at resting and relax with no problems at all, right? So we're sitting here at resting membrane potential. But when the cell is stimulated, we're going to open sodium channels. Okay? Yay, sodium, we're familiar with that. We like sodium channels, right? So what we're going to do is when the cell is stimulated, sodium channels open and we see depolarization occurring. Again, let's go ahead and annotate that a little bit. So we'll come over here and we'll say that when the cell is stimulated, we are going to open sodium channels. Something familiar, I like that. Okay, so sodium channels. Sodium is going to rush into the cell and it's going to cause the cell to depolarize. So what we see is we just see a big depolarization of that cardiac muscle cell. All right? Now, those ion channels, like most ion channels on excitable cells, are voltage gated, meaning that they open and close in response to different membrane potentials. Okay? This guy opens when it's stimulated, okay? It opens when it's stimulated and it closes at around positive 20 millivolts. So at around positive 20 millivolts, we see that those sodium channels are going to start to close. And we're going to see that the action potential turns around a little bit. Okay, so at around positive 20 millivolts, we see that the sodium channels are closed. start thinking that this is uninteresting and boring, because it gets fun, okay? Turns out that on cardiac muscle cells, we have two types of potassium channels. We have what we call fast potassium channels, and we have slow potassium channels, okay? That slow and that fast describe the speed with which they open. So, which one do you think opens first, slow or fast? Fast, right? The fast potassium channels are going to open. And they do that, right? The fast potassium channels open. And we see that we start to have a slight repolarization of the cell, okay? So here, I'm just going to put numbers, well, actually, I'm not going to do that. I'm just going to put it in the same step. So number 2, we're going to see that fast potassium channels open, okay? But not only do they open fast, they close fast, okay? So they're only open for a short period of time and then they close again. So what we see is we see that we have this sort of plateau that starts to occur, okay? So we see that we have potassium flowing through the cell. This is an increase in sodium right here. And then we have this kind of plateau. A plateau is due to a couple of things. It's due to the decrease in potassium permeability, but also at that point we open calcium channels. I know, right? It's a wacky one, but we open calcium channels. So what's happening here is we start to see a slight decrease in potassium, but we also see an increase in calcium permeability right here. So remember that over here, calcium, when we increase that permeability, it caused a big depolarization. So now I kind of have potassium just kind of eking its way out of the cell, and I have calcium eking its way into the cell, and those two things kind of balance each other out. So what that does is it causes the membrane potential to be relatively stable for just a little bit. So we get a little bit of a plateau that occurs right here, okay? So I'm going to go ahead and put a 3 right there. And I'm going to say, what am I going to say? Calcium and potassium flow across the membrane. And that leads to a plateau, a flat area in the membrane potential. That leads to a plateau, okay? But then, after a little while, we see that those slow potassium channels open. Okay, we see that those slow potassium channels open in mass, and then we have a repolarization of the cell. So now we see that we have, again, an increase in potassium, and we see a decrease in permeability to calcium, because those calcium channels don't stay open for very long, and we have a change in the membrane potential again. So we'll call that number 4 over here, and number 4 is that slow potassium channels open and calcium channels close, and that causes return to rest. Okay. And then the whole thing is over. Okay. So it's a wacky looking action potential, because it's not just an up and down sort of a thing. We've included a little bit of a plateau right here, this flat area, because we have this brief period of time where we have both potassium and calcium flowing across the membrane, okay? The whole thing takes a long time. We're looking at like almost 300 milliseconds. From beginning to end, we're looking at about 300 milliseconds. In a skeletal muscle, by contrast, you're looking at an entire action potential lasting about 7 or 8 milliseconds. So this is really long time compared to what we see in skeletal muscle. Why would cardiac muscle have such a long action potential? Why would this occur? Let's think back to skeletal muscle for a minute. With skeletal muscle, we saw that you could stimulate a muscle over and over and over again. And if it wasn't fully relaxed, what would it do? It would contract again and it would get more forceful, right? And then you could stimulate it again before it relaxed and it would contract more forcefully. And if it wasn't completely relaxed and you stimulated again, it contracted more forcefully until it reached a maximum tension. But if you stimulated it fast enough, did the skeletal muscle ever relax? No, what do we call that when the skeletal muscle just, that constant state of contraction with no relaxation? What? Tetanus, yeah, we called it tetanus, right? Or tetany, right? You can reach tetany. We called it tetanus, right? That's really useful for skeletal muscle because I have to hold things with skeletal muscle, right? When I hold this like this, I have to put my biceps into tetanus so that I can hold this in place, right? It's not so useful for my heart, right? My heart really shouldn't go into tetanus because I need it to completely relax between contractions, right? Because the heart has to fill with blood. Between every contraction, those ventricles have to fill with blood. And then I have to contract and I have to pump that blood out of the heart. I have to relax, let the heart fill, and then pump the blood. I have to relax and let the heart fill and pump the blood over and over and over again for the whole of my life. I have to let it relax, fill with blood, and contract. If I do this, it ain't going to fill with blood, and it's certainly not going to be able to pump any blood. And that's not a good situation, right? So what this long action potential does is it creates a situation where even if I were trying to stimulate the heart at a faster rate, let's say something went really crazy with my pacemaker cells, and they just start launching all sorts of action potentials, the cardiac muscle says, hey, step on the brakes a little bit, buddy. We got to slow this down. We have to completely relax between contractions, right? So this long action potential and the fact that we have these fast and slow potassium channels and that plateau that's created by the calcium channels in here is going to really just cause the action potentials to slow down, okay? And that allows the heart to relax and completely fill with blood between contractions. Does that make sense? Has to happen in the heart or else you're getting the deep six, as my grandma would have said. You're going 6 feet underground. That's what my grandma used to say. Call her before she died. I said, how are you feeling today, Nana? She said, I'm ready for the deep six.
Oh, man.
Yeah, she was harsh. Either that or she was ready to move to Box City, as she said. And I said, you can't say that, Nana. I said, I'm ready for Box City.
Oh, my
said,
God.
Nana. So when she passed away last year, she was 93 when she passed away. She passed away, so she finally went to Box City. All right. I know there's a lot here. I know that one action potential in 50A felt like a lot. I just gave you 2 today. So I know this is going to take some time to process. I know that the questions may not come immediately. It's definitely not something that you're going to be able to take a look at in your notes and just say, yeah, I got it. Like, you got to go to your book and you got to read about this and you got to rewrite it and you got to tell the story over and over and over again until it starts to make sense. Because there is a lot here, and I understand that, but it's something that you've got to dig into and you've got to take ownership. Just rereading your notes on it is not going to be enough. If you want to really understand this, you got to go to your book, you got to go to other sources, and you've got to spend time kind of decoding what we've been talking about here today. I like to think that I'm perfectly clear, but I know that you're going to walk out of here and be like, yeah, I got questions, and that's okay. But we got to make sure that those questions get answered, right? You can take the first steps by correlating what we have here with the notes that you've taken today with your book, and then we can answer questions as they kind of come up, okay? But both of these are really important things that relate to how the heart functions. And that makes the heart such a unique organ in the body. So, with that said, what we're going to do, now that we understand that there are these autorhythmic cells in the heart that launch action potentials, we're going to look in lab today away from the cellular stuff. I have a little bit more cellular stuff to talk about, but not much. But we're going to take a look away from the cellular stuff, and we're going to look at the heart as a whole, which is actually probably going to relate to us a lot more than this stuff will, at least on the day-to-day. But this stuff is important because the heart is affected by lots of different things, and if you understand how it works at a cellular level, you'll understand how those things affect it and how the drugs that we use to treat those things actually work, because we're leveraging all of this when we prescribe drugs to patients. All right, so I think we're out of time. I think our brains are sufficiently fried for a Friday morning, so we'll go ahead and end there. We'll continue a little bit of this in lab.